Welcome to the fifth tutorial on dynamic system modeling and control. This tutorial, the official title of the tutorial is Introduction to Modelica. In some ways it serves as an introduction to two things that are fairly separate, one of them being Modelica, the other one being the modeling of rotational mechanical systems. Once again, my name is Hussam Fathi, and it's a pleasure to have you in this tutorial. So, as I mentioned, the tutorial has two big goals. The first one is to build a state space model of a simple rotational mechanical system. So we want to essentially transition at this point from having done an example on translational mechanical systems to now also doing an example on rotational mechanical systems, so that you're introduced to rotational mechanical systems. And the second goal is to introduce the Modelica language for dynamic system modeling. These are two fairly distinct goals, but I've rolled them into a single tutorial to sort of kill two birds with one stone. So I'm going to start by talking about the first goal. I want to build a state space model of a very simple rotational mechanical system. The system that I'm interested in here is essentially a pendulum. I'm going to look at a foundation that is fixed here, and attached to this foundation is a pendulum of mass m and length L, and the pendulum is acted upon by an external torque. Perhaps it's attached to a shaft that is torqued, and the torque is u of t, and I'm interested in seeing both how the pendulum would oscillate and vibrate freely if this torque was zero, and how the pendulum oscillates and vibrates under the influence of this torque. I'm interested specifically in the angle between the pendulum and the vertical, which I call y of t. If you recall from the previous tutorial, there are 5 steps to developing a state space representation of a dynamic system. The first step is to identify the inputs, and we've already identified the input in this case. It is the torque acting on the pendulum, u of t. The second step is to identify the outputs, and we've already identified the output in this case. It is the angle between the pendulum and the vertical, y of t. Now the third step is to identify state variables. Now this is a rotational mechanical system. It stores energy due to the rotation of the pendulum, and it stores two distinct kinds of energy. First of all, as the mass rotates, as the mass of the pendulum rotates, it rises upwards, and therefore it stores potential energy. Secondly, as the mass moves, it stores kinetic energy. In this particular case, the potential energy is a function of the angle of the pendulum relative to the vertical, and the kinetic energy is a function of the angular velocity of the pendulum. So it makes sense to make the state variables, number one, the angle of the pendulum with respect to the vertical line, the downwards vertical line to be specific, and I'm going to make that positive counterclockwise. The second state variable is the angular velocity of the pendulum, and I'm also going to make that positive counterclockwise. So at this point we've identified the state variables, and we're done with step number 3. Step number 4 is to write down the state equations. I want to write down an equation for x1 dot and an equation for x2 dot. The equation for x1 dot is very easy. The rate of change of pendulum angle with respect to time is just angular velocity, and so therefore x1 dot has to equal x2. The second state equation is the state equation for x2 dot, which is the rate of change of angular velocity with respect to time, which is angular acceleration. To write a state equation for angular acceleration, I need to calculate the summation of moments acting on this pendulum, and essentially use the law of motion in the rotational coordinate frame, which says that the summation of moments is equal to the angular acceleration of the pendulum multiplied by its moment of inertia. Now this law of motion applies only in 2 cases, and we need to be very careful. The summation of moments on a rigid body around the center of gravity of the rigid body equals the moment of inertia of the rigid body around its center of gravity multiplied by angular acceleration. This is true. It is also true that the summation of moments on a rigid body around a fixed point in space that the rigid body is hinged at equals the moment of inertia of the rigid body around that point multiplied by its angular acceleration. Fortunately, in this case, we do have a pendulum that is hinged around a fixed point in space, so we can apply this law of motion. But in order to do that, of course, as we've done before, we have to draw a free body diagram. So I'm going to remove everything but the pendulum here, and I want to draw the forces and the moments acting on the pendulum. Obviously, there is the input torque, U of t. There are also reaction forces in the x direction and in the y direction from the support. And in addition to that, there's the force of gravity, and we can break down this force of gravity into a component that is equal to mass times gravity times the cosine of the angle with respect to the vertical, and another component that is equal to mass times gravity times the sine of the angle that the pendulum makes with respect to the vertical. The hinge point for this pendulum is the point at which the reaction forces Rx and Ry are applied. I want to take the summation of moments around this hinge point, and I want to make that summation of moments equal to the inertia of the pendulum around that hinge point multiplied by angular acceleration. The inertia of the pendulum around the hinge point is just the mass of the pendulum multiplied by the length of the pendulum squared. So when I think about that and I apply that, I find that the angular acceleration of the pendulum is equal to 1 over the inertia of the pendulum, which is ml squared, multiplied by the summation of moments around the hinge point. One moment around the hinge point is the input torque U of t. The other moment around the hinge point is mg sine of theta multiplied by the length L. These are the only moments around the hinge point because mg cosine of theta does not, that particular component of the gravitational force passes through the hinge point, so it doesn't apply a moment relative to it. Also, the reaction forces Rx and Ry do not apply a moment around the hinge point because they pass through the hinge point. So at this point, I'm done writing state equations, and the only thing that is left is to write the output equation for this pendulum. The output was the angle y between the pendulum and the vertical that also happens to be the same as the state x1, so y is equal to x1. Whatever I've boxed here is the complete set of state and output equations for this pendulum. This is the state space model. So what we've accomplished so far is we've built a very simple state space representation for the dynamics of a very simple rotational mechanical system. So we've accomplished one of the two things we wanted to accomplish in this tutorial, which is to go through a simple rotational mechanical system and derive its state space model. But I want to now move on to the fairly unrelated goal that I'm just trying to, kill with the same stone here, kill two birds with the same stone, which is to introduce you to the Modelica language. The Modelica language is a standard language that you can use to express system dynamics in a form that computer compilers designed for Modelica will understand. And you can write your dynamic model in Modelica, and then there are tools out there that will compile this Modelica model and simulate it for you, and combine it with a solver and simulate it for you. I could be giving you a tutorial right now on how to construct a solver for a set of differential equations, because that's what we're doing. And we could be talking about the Euler method for solving differential equations and Runge-Kutta methods, etc. And we hopefully will get to that potentially in one of the future tutorials if we have enough time in these tutorials. But what I find very convenient is, instead of going to the details of how to construct a solver, I find it very convenient in constructing these tutorials to basically show you how to simulate models in Modelica without having to worry about how to build a solver for these models, how to actually build a piece of code that simulates these models. The reason why I find that very convenient is because as you go through these tutorials, I really want you to simulate models in Modelica of things that you're modeling, just so that you can see how they behave and you can see if the models give you the kind of behavior that you expect. This will help you acquire a lot of intuition regarding the behavior of dynamic systems, which will be particularly valuable when we start moving to the next big section of the tutorials, the sort of mid-section of the tutorials, which focuses on dynamic system analysis. So with that preamble in mind, I want to show you a Modelica environment. There are several Modelica environments. There are several excellent Modelica environments. If you're watching this tutorial because you are an ME 450 student at Penn State, we have a Modelica environment by the name Dymola installed in the mechanical engineering lab in Reber. You might want to check it out. But if you're watching this tutorial from elsewhere, or if you're trying to work on homework problems from home and you're not in Reber, if you're at Penn State, there is a Modelica environment called Open Modelica that you can download for free off the web. So what I'm going to do now is I'm going to switch to Open Modelica. Open Modelica and Modelica in general is a fairly rich set of environments for dynamic system modeling. I'm not going to be showing you everything, but I will show you the basics. I've started the Open Modelica connection editor, OM edit here. What I'm going to do is I'm going to go to the file menu and I'm going to say new model, and I'm going to call the model pendulum. Okay, so so my model name is pendulum, and I'm not going to insert it in any package. I get a blank screen, and we will see all the interesting things that you can do in the blank screen in the future. I want to switch from the blank screen, which is currently in diagram view. I want to switch to text view, which shows me the actual code underneath the blank screen. So far, I've just created a model called pendulum, and I've ended the model, and that's it. Now I want to actually create the model. The first thing I'm going to do is I'm going to create the model parameters, and then I'm going to create the model variables, and then I'm going to write down the set of equations governing the model. And then finally, I'm going to simulate the model and see what it tells me. So the model has parameters: the mass of the pendulum, the length of the pendulum. Those are basically the two big parameters that we need to think about here. So I'm going to enter a parameter, and it is a real number. Now, Modelica has the ability, by the way, to understand SI units. So I could have replaced real with a little piece of code that says, no, actually, this is a mass and it's in kilograms. But to keep things simple, I'm just going to say it's a real number, and I'm not worried about its units right now, which is fairly sloppy given the capability of the Modelica language, but I'm just trying to keep the example as simple as possible. So there's a parameter real number, and I'm going to call it m, and it's the mass of the pendulum, and I'm going to make it equal to 1. And I'm going to throw a little comment here and basically say that this is the mass of the pendulum. Okay? And then I'm going to throw in another parameter, and it's also a real number, and it's L, and it's equal to, let's say, 1 for simplicity. And I'm going to say this is the length of the pendulum. Okay? Now, I've defined my parameters. The next thing I need to define is my set of variables. I need to define my state variables, my input variables, my output variables. Let me begin with the input variables. So I'm going to have a variable, and I'm going to call it u, and it's not a parameter anymore, so it's just a real number, and it's called u. And I'm going to say that that is my my input torque, and then I'm going to have a real number y, and that is my output angular displacement. And then finally, as far as the state variables are concerned, I'm going to have a real x1, and I'm going to say that that is my pendulum angular displacement, also the same as y, and I have a real x2, and that is the pendulum angular velocity. Okay, and now I'm done defining all my variables. Now, state variables, Modelica doesn't actually make a distinction explicitly between state variables and other variables, and this is partly due to the structure of Modelica and the fact that it's designed to solve any differential algebraic equation, and we hopefully will find time to get into what that means later in this set of tutorials, I hope. But essentially, state variables are variables that are governed by differential equations, and so they can have initial conditions. So I'm going to go under real x1, and I'm going to give it an initial condition, and I'm going to say that this initial condition, I say that it is the start, it is the starting value of x1, and I'm going to set it to, let's say, 1 radian. Whereas the initial condition for angular velocity, I'm going to say, is 0 radians per second. Okay? So when I open parentheses and I say start, what I'm saying is that this variable has an initial condition, and I'm actually specifying it. At this point, I'm done specifying all of my variables and all of my parameters. The only thing that's left is for me to specify the equations governing this pendulum. Literally my state and output equations, literally my state space model. So I open a new section of code that starts with the word equation. And now what I'm going to say is I'm going to say, well, my governing equations are x1 dot is equal to x2, x2 dot is u minus mgl sine theta divided by ml squared, and y is equal to x1. The operator for a derivative with respect to time in Modelica is der. So what I'm saying is that the derivative of x1 is equal to x2. And the derivative of x2 is equal to, first of all, u minus m times the gravitational constant. I forgot to define the gravitational constant. I'm going to define a parameter, real g is equal to 9.81, and that is the acceleration of gravity. And again, if I used slightly more sophisticated Modelica code, I'd be able to basically say that that is an acceleration in SI units and so on and so forth, but I'm not going to do that here. I'm just trying to keep things simple. So I have u minus m times g times l multiplied by the sine of x1, okay? And then that whole shebang divided by mass times length squared, so divided by m times l squared, and that's my second state equation. And then my output equation is that y is equal to x1, and the only thing I have not specified here is the input u. And for this initial study, I just want to see what happens when the pendulum is just released from rest at 1 radian and let it vibrates. So I'm going to make my input u equal to 0. And those are my 4 equations, my 2 state equations, 1 output equation, and then 1 equation specifying the input, dictating the input. If I click on the check button here, Open Modelica checks the equations for me, and it says I have 4 equations and 4 unknowns. Let's not worry about what trivial means here, how many of those equations are trivial and what that means. It basically says I have 4 equations and 4 unknowns, which is really great. And so basically it's ready to compile this model and run it for me. I'm going to hit the run button, and I'm going to simulate this model for about 10 seconds here and see what I get. So if I hit simulate, it compiles the model and then it runs it. And it gives me a graphical screen, and notice how I've switched from the modeling panel to the plotting panel. Now I can plot x1, which is the angle, as a function of time, and you notice how the pendulum oscillates beautifully, which is what we expect a pendulum to do, between +1 and -1 radians. I can look at the angular velocity as a function of time, and I see how the pendulum as its position varies between + and -1 radians per second, the angular velocity, which is the slope of angular position as a function of time, varies between + and -3 radians per second here. Yeah, almost exactly 3 radians per second. And there's a reason for that. We will find out later in the class that very approximately, if you linearize a pendulum model, around small angles, which the initial condition for this pendulum is not a small angle, but if you were to approximate the pendulum as having small angle initial conditions, the natural frequency of the pendulum is g over L, and so the position will equal initial position multiplied by cosine of the square root of g over L times time, the natural frequency, the square root of g over L, in radians per second. When you take the derivative of that, the angular velocity will equal that quantity multiplied by the square root of g over L, and instead of cosine it becomes negative sine of time. And so the square root of g over L, the natural frequency here, happens to be somewhere close. You know, g is 9.81, length is 1, and so square root of g over L is somewhere close to 3 radians per second, and so we would expect the velocity to peak around 3 radians per second. That's not exactly correct. The square root of 9.81 is not exactly 3, but remember the argument I just made is based on a linearized version of this pendulum, and we will go over all of that later in this set of tutorials in a lot more detail. One of the really neat things about Open Modelica is that it allows us to plot state variables against one another. So if I hit the x as a function of y plot, now I can plot two variables against one another as opposed to against time. Now x1 is on the x-axis and x2 is on the y-axis. The pendulum goes through an almost perfectly elliptical trajectory here in what is known as the state space, and also this is sometimes known as a phase plot, a phase plane plot, or a phase plot. And so as you see, we have beautiful oscillations where angular position increases and angular velocity is therefore positive, and then angular position decreases and angular velocity is negative, and we keep going around this ellipse in a very, very beautiful way. So we've simulated this pendulum with an initial condition but without a torque. I want to apply a torque now, so I want to go back to my simulation model, and instead of u is equal to 0, I want to apply a torque, and I'm going to make it a very slow torque relative to the natural period of oscillation of this pendulum. So I'm going to make the torque u equal to the sine of, let's say, 0.05 multiplied by time, and the symbol for the expression for time in Modelica is just time, T-I-M-E, lowercase. And so what that means is that the torque that is applied is sinusoidal, and it has a period of 0.0. It has a frequency of 0.05 radians per second. I'm going to simulate this again. I'm going to simulate this over the course of 100 seconds now, and I want to see what I get. And Open Modelica compiles the model and runs it. And now let's say this x1 is the same as y. So regardless of whether I plot x1 or y, I'm getting the same plot. This is the angular displacement of the pendulum as a function of time. You notice how I have two sinusoidal patterns superimposed on one another. The relatively fast pattern is the natural oscillation of the pendulum due to the initial condition. But on top of that, I have a much slower sinusoidal oscillation due to the applied torque. I can zoom into this graph to see the details of the oscillations over certain time durations if I want, and I can go back and fit the whole plot in my screen again. So it's very convenient to be able to play with a model like this and ask what-if questions and simulate it under different conditions. Underneath all of this lies an engine that compiles the code that I just wrote and combines it with a solver and solves the resulting differential equations. And this piece of code has a certain level of numerical accuracy associated with it, and there are ways that you can adjust its numerical accuracy and so on. Those are details that are important, but what I wanted to show you was how to use the Modelica language to represent a model of a very simple dynamic system. There's a lot more to Modelica than this, there's a lot more to Open Modelica than this, but I just wanted to show you the basics. So what have we learned from this tutorial? We've learned, number one, how to build very simple models of rotational mechanical systems. The other thing is we've learned how to construct these models in Modelica and simulate them and play with them, basically. Thank you very much for watching this tutorial, and I look forward to going through the next tutorial with you. Thank you.